Okay, good morning, everyone. I see that the participants list is slowly filling out, so hopefully we can get everyone on board in the next couple of minutes. Yeah, perhaps since it's past 9:15, we can begin the webinar. So good morning, everyone, again, and very welcome to this webinar from the CHEERS CLC project. CHEERS is short for Chinese European Emissions Reducing Solutions. It's an international R&D project to demonstrate a second generation CCS technology at a relevant size, taking it up to TRL 7. The project consortium consists of European partners, including Total and IFPEN, Silesian University, SINTEF, and Bologna. The Chinese partners include Tsinghua University, Zhejiang University, and the Dongfang Boiler Group. So the key deliverable of this project is to design, construct, and operate a chemical looping combustion 3 megawatt demo unit and validate the CLC technology with petcoke and lignite feedstock. So now I will hand over the word to Stefan Berthelin from IFPEN, who will continue to present more details about the project and especially more details about the work of Work Package 5, which this webinar is about.
Thank you, Anna. Good morning, everyone. Maybe just before going to the presentation of the day, I can just provide a short update about the construction of the demo plant. So as you can see on this picture, the construction is almost finished. So now the next step will be the commissioning of the unit, and the startup is expected to be started at the beginning of April. So we could provide more information during this year. So now we'll start with the webinar of the day. So I'm Stefan Berthelin, so I'm the CLC project leader at IFP Énergie Nouvelle and work package leader in CHEERS. And today we will present the results of the work package 5 of the CHEERS project, which deals with assessments of the CLC process at industrial scale. So in this picture, you can see my colleagues who will present you the different parts of these work packages. Some colleagues from SINTEF Energy, Total Energy, and IFP Énergie Nouvelle. Before going to their interesting presentation, I will just briefly introduce the work done in this work package and how it has been organized. So the main objective of this work package was to provide techno-economic assessments of the CLC technology. So for that, we have addressed different design cases relevant for industrial needs. So we have covered both industrial needs to decarbonize actually industries, and also power supplies as for the design. And the CLC has been benchmarked with reference technology. So you will see we have also designed NGCC and CFB technologies for this benchmark. And to provide a full assessment of the project, we have also considered the full CCS chain. So it means including transport and storage of the CO2, and also environmental perspectives thanks to life cycle assessments. So the work package was divided into 3 different tasks during the project, as you can see on this slide. So the first step was to provide a model for the fuel reactor, which will be available at large scale. So it was the first 3D. As you can see, it has been done at the beginning of the project, years 2018, 2019. So this was also important for the design of the demo unit, actually, because for us, the demo unit is also large scale. So the result for this case was also used for the design of the demo plant. And then based on these models, we have provided a process simulation, we perform process simulation to provide all the data needed for the economic assessment. So this will be the second part of the presentation. And finally, based on these elements, we have made a TEA, economic study. So we'll see, we have several presentations on that. So here you have the webinar presentation of the day. So we'll start with Nicolas for the modeling, and Catherine for the process simulation. And then regarding the benchmark, we'll have really the economic evaluation done by Vincent, then the result of the benchmark study, including the full CCS chain by Simon. And then to conclude this webinar, Elodie will present the results of life cycle assessment. So now I will let the floor to Nicolas for the first part of this presentation about the reactor models.
Okay, can you hear me well?
Yeah.
Yeah, okay. So thank you, Stéphane. So I'm Nicolas Vin from IFPN, research engineer, and today I will talk about, as part of the deliverable 5.1 about the CLC reactor modeling. I will talk about how we develop with a multi-scale approach a fuel reactor modeling of an industrial unit. So, yeah, so so as Stéphane already said, for technico-economic studies, we need a fuel reactor model, you know, to help for the development. And to do that, we elaborate a strategy in 4 parts. The first part is the development of a first model of a batch unit that we have already at IFPN. The second step is to validate the model on continuous operation based on the experimental result we also have at IFPN. The first step is to upgrade the model to take into account the specificity of the industrial scale. And so by adding an appropriate hydrodynamics, because the hydrodynamics between the IFPN units and the industrial scale unit is different. So we need to take it in the model, take it into account. And the final thing, which has not been done, is to validate the model of the industrial fuel reactor. Sorry, by taking into account the experiments done at the demonstration the CHEERS unit. Sorry. Next slide, please, Stefan. Yeah, so to talk about the model, so the model is divided in several parts, several banks. So, for example, we have a bank which is linked to the reaction. So all of the reactions are included in the model. So just the different species reacting between them. We have also a kinetic bank, which contains the kinetic parameters of each reaction we mentioned in the reaction bank. We have a solid bank, which will calculate the source term. It means that the species will be generated during the reactions. We have a compound banks where we will have all of the species involved in the model. We have also a hydrodynamic bank who will take into account the specific hydrodynamic of the unit we will model. So, for example, for the IFPN units, we will take in the model a bubbling bed hydrodynamic, whereas in the industrial unit, we will take into account a turbulent bed hydrodynamic. So it's 2 different hydrodynamics who have been implemented in the model. And in this part, we are also calculating some different parameters, correlation, who are used in order to take into account each hydrodynamic we want. And so excuse me, Stefan. And finally, we have a core who will get depending on which type of unit we want to simulate. For example, if you want to simulate the batch unit or the continuous unit, we will. It's easy in the model to split and to take into account the specific hydrodynamic in the unit we want to model. I mean the fuel reactor. Sorry. Yeah, so you can next slide, please, Stefan. Yeah, so to develop the model, we as I said, we used 2 different units we have at IFPN. So the first unit, it's a batch unit. You can see on the top of the slides, where we can easily study the impact of different parameters such as temperature, water content, CO2 inlet content, and, for example, petcock diameter. So as you can see here, we have the steam content effect, which is quite huge on the petcock conversion, and also the temperature effect on the petcock conversion. And the second unit we have to perform the experiment to get some experimental data. It's a 10 kilowatt unit at IFPN, which is a circulating unit. And we can also, in this unit, study different parameters, such as temperature, water content, petcock flow rate, and the oxygen carrier flow rate. Yeah, next slide, please, Stefan. So based on these experiments, we have calibrated the fuel reactor model. So on the top of the slide, you have the experimental result versus the modeling results based on the experimental data we got in the batch unit. So as you can see, we have quite a good prediction of the parameters impact, except for the petcock conversion over 80%, where we have a slight overestimation. And based on this work, so we based on this experimental data, we extract some kinetic parameters. And based on that, we developed a model for the continuous unit. And you can see on the bottom of the slide that without changing any of the parameters, of the kinetic parameters we got from the batch unit, we were able to simulate well to represent well the experimental data we got. So it means that we have a good extrapolation to the pilot scale. So it means that the physics is well represented, and that the kinetic parameters we got from the batch unit are intrinsic kinetic parameters, because we did not need to change any of them to get some good results when we try to simulate our 10 kilowatt continuous unit. Yeah, so next slide, please, Stefan. So the third part of the strategy was to model the fuel reactor of an industrial unit. So as I said at the beginning, the hydrodynamics in this industrial unit is a bit different from the hydrodynamic in our IFPN units. So we need to implement in the model a turbulent fluidized bed reactor instead of bubbling, as I said previously. And so to do that, we worked with Tom Widwatt, who has done his PhD at the Humboldt University with Total Energy. And based on the work of Tom, we updated the correlations in the model to take into account that the hydrodynamic is a bit different, and it's a hydrodynamic of a turbulent fluidized bed reactor. So as you can see on the bottom of the slide, we have the correlation who have been updated as just as examples. But this work has shown that we can keep the model, I mean, the material balance of the model to take into account the turbulent fluidized bed reactor, but just we need to adapt the correlations for the hydrodynamic part. Yeah, so next slide, please, Stefan. Yeah, so for this work, so we implement in the code the correct correlations, so proposed by Tom, and we were able to simulate the fuel reactor performance. So based on the operating condition of the design of the fuel reactor, we were able to model the result. So the fuel reactor model gives a result of 64.7% for the petcock conversion. And the process target in the same operating condition, the target was at 60%. So it means that for a first try, it's quite encouraging. And now the next step is to validate the result on the experimental data we will get on the Cheers demo unit. So to conclude about this work, so we develop a multi-scale approach to step-by-step develop a fuel reactor model of the industrial unit. So as I said, we first have a model for the fuel reactor of a batch unit, so which is in the bubbling fluidized bed, the hydrodynamic. Then, based on the work we got on the batch unit, we were able to develop a model for the continuous unit based on the experimental data we got on the batch unit, and we are also able to validate the model on the experimental data we get on the continuous unit. And the last step was to modelize the fuel reactor of the industrial scale unit So by adapting the good hydrodynamic in the model, so by applying hydrodynamic of a turbulent fluidized bed. And so based on that, we are able to modelize the fuel reactor of industrial unit, which now needs the validation on the Cheers demo unit. And yes, that's all. Just to finish, yeah, all of the work we got from the industrial scale unit was based also, as I said, on the work of Tom Winwatt from the Hamburg University, who helped us to implement in the model the correct correlation for turbulent fluidized bed. Yeah, so thank you very much. And I know it is quite short presentation, so don't hesitate to send me an email if you want some more explanation about more details about the model or anything. Thank you. I think you are muted, Stefan.
Sorry, I was muted. Yes, I just want to add that if you can also use the chat of the Zoom chat if you have a question for Nicolas, and I will try to answer during the webinar. Okay, thank you, Nicolas. So now we can go to the next presentation. Presentation from Catherine about the process simulation.
Good morning, everyone. Can you hear me correctly?
Yeah.
Okay, so good morning and good afternoon to our partners in China. So I'm Catherine Laroche from IFPN. I was in charge of the process studies for the Cheers project. So as Nicolas presented, so the first step was the fuel reactor modeling, and now with the second deliverable, the objective was to go to the modeling of the full plant size, and so we performed the process simulation of the CLC plant at industrial scale, and it was applied to two different settings. So it was the refining and the power sector, as you will see in the next slide, please. So the CLC plant at industrial scale, we decided to have two different design cases in order to assess the performances of the process at two different scales. So we have the first design case was for the refinery. The idea was to have two different generations. So we have a generation of steam, 100 tons per hour of steam at 500 degrees and 100 bar. And the unit was also used to provide electricity. So 50 megawatt of electricity. So it was really to provide the utilities for the refinery. And the second application case was for the power sector. So it was a 200 megawatt electricity generation. So on the right, what we see is the block diagram of the CLC at the industrial scale. So we have the CLC is fueled with petcoke, so solid fuel. We have ilmenite, which is the oxygen carrier that is used and considered in this study. So both are injected into the CLC reaction section. We see in the center. We have two different flue gas coming out from, one is coming out from the air reactor, so it's depleted air. It has to be to get rid of the different particles or fines that can be present in this stream. So we have a D-dust, and then we have the second flue gas outside from the fuel reactor. So this flue gas will contain some NOx, SOx, and also some particles. So you need to have a deeper flue gas treatment. So you have D-NOx, you have D-dust, and you have D-SOx. And then you can have your CO2, and this CO2 will go into the CO2 compression stages so that it can be then stored and further sequestrated. And around the CLC reaction section, because we have hot streams, we have the hot oxygen carrier that is circulating. We have also the different hot flue gases, we can recover heat. And this heat is recovered through different steam cycles, and this steam will go to turbine in order to produce electricity. So this is the basic of the whole industrial scale for the CLC plant. And this plant will be benchmarked to different technology. So if you go to the next slide, please. We see the two different reference technologies that were considered to benchmark the CLC. So the first one was the natural gas combined cycle, so NGCC. We have here the fuel is natural gas, which is fuel to gas turbine. So we have a gas turbine, which will produce electricity. And we also have a heat recovery, which will generate steam. And from this steam, you can also have steam turbine that will generate electricity. In the end, you will also generate some CO2. So you have to couple this NGCC to a standard amine CO2 capture unit prior to the CO2 compression stage. So for this amine CO2 capture unit and for the NGCC, two different amine were considered. So the very conventional MEA and one more advanced solvent, which is the piperazine with the AMP. So this was the first reference technology, and we have also the second one, which is which use petcoke similar to CLC, which use petcoke as a solid fuel, and this is CFB, which means circulated fluidized bed. So it's quite well known for the case of coal and for the power sector. So in this, you have a furnace in which petcoke is entrained, and you will also recover heat through steam cycle and steam turbine. And once again, in the flue gas, you have only one flue gas stream in this, so you have to get rid of the different particles, the NOx, and you will have to get to capture the CO2 using an amine CO2 capture unit. And in this case, we considered only MEA standard, MEA solvent. Okay, so this was the two different reference case. So we can go to the next slide, please. For the process simulation, so of course, process simulation was performed for the different technologies. So I will only show you the overall process simulation sheet that we have with Aspen Plus for the CLC case. So we see on the left the CLC block. So this is really the where you have the reaction section, the different circulation of the oxygen carrier. So the oxidation and then reduction of this oxygen carrier. And you have one important thing which is new compared to the reactor modeling. This is all what is related to the heat recovery and the flue gas treatment that you see here up in the red box. So with the heat recovery, you will have many different heat exchanger. You will generate steam, you will reheat steam, and with this steam, you go down to the steam turbines to generate electricity. And after the flue gas treatment, you have a completely clean CO2 that can go into the CO2 compression stage, so that you go up to 110 bar, which was the design case that was considered, and CO2 was cleaned in order to meet the specification for storage. Okay, so we can now go to the next slide. So it's just a focus on the heat recovery and flue gas treatment, for instance, for the refinery case, but it is very similar for the power case. So we see here that we have three different streams. So these are the hot streams. So the first one is the depleted air coming out from the air reactor. So we exit this reactor at a high temperature. It's not very far from 1000 degrees C. So of course you will be able to recover heat using heat exchanger in order to produce, generate steam, to reheat, superheat steam. And after, you will have different steps that are needed to, for instance, to preheat the different streams that you will inject into the CLC section. For instance, you will inject air, so you have to preheat this air. And at the very end, you will get rid of the different particles. Then the second stream is the flue gas coming out from the fuel reactor. So on this one, you have first, of course, heat recovery. And then secondly, you will have all the flue gas treatment, denox, dedust, and desox. And the third stream is the oxygen carrier that will be circulating inside the CLC. And on this one again, you will recover heat using heat exchanger by steam. And this steam will go there in the steam cycle and the steam turbines. We can go to the next slide, please. For the CLC section itself, our strategy for the simulation was to couple three different tools. So we have Aspen Plus. So it's winter time. So we have Aspen Plus simulation. For this one, we need some specific parameters that will come from the different other tools. So we have on the left Aspen Plus simulation. On the top, we have our own hydrodynamics model, which will be used to predict the different solid separation efficiency, solid separation efficiency of the cyclone, of the carbon stripper, and which will be used as well to define the size of the reactor. So with this reactor design, we have the sizes, so we know the residence time of the oxygen carrier, and coupling this information with the composition of the different stream from the Aspen Plus simulation, we can enter this into the fuel reactor model that was delivered in the work package, the deliverable 5.1. And from this, we get the fuel conversion per pass, which is then a parameter that is used in the Aspen Plus simulation. So we have this strategy needs to have different back and forth in order to converge and to a stabilized simulation. So this is how we run the simulation. And now I think we will just have a brief overview of the, I talked about reactor size. So we see here just to have an idea of the different sizes of the air reactor on the left and the fuel reactor on the right for the different application. So we have first the power case, then the refinery, and then just to compare the demo unit in blue. So what is seen here is that globally the height is not very different for the different cases. We have approximately something which is between 30 meters for the fuel reactor up to 40 meters for the air reactor. What is changing is the diameter. So the demo unit will be very representative from that perspective, because the height is similar to the height of an industrial scale, and which is very important for the hydrodynamic point of view. Now we will go to the performance and the comparison of the performance of the CLC plant to the reference technologies. So I will just give the result for the power case, where the objective was to deliver 200 megawatts of electricity. So to deliver this 200 megawatts of electricity, we see in orange the different value for the thermal power input. So the CLC is not far from 500 megawatt thermal megawatt, and this is a value which is ranging between the CFB, which requires more than 600 megawatt thermal megawatt, and the NGCC, which is more efficient because it requires only 450 megawatts of thermal input to provide the same 200 megawatts of electricity. So you see here down the different net electric efficiency. We have overall 38.4% of net electric efficiency for the CLC case, compared to a little bit less than 32% for CFB coupled to CO2 capture. And the most efficient is NGCC coupled to CO2 capture with something very close to 47%. And if we go to the CO2 capture efficiency now, so we see here in the graph that we have a CO2 capture ratio that was reaching 97% for the CLC case. For the two other benchmark technology, reference technology, since we used a very conventional CO2 capture design, it was based on a 90% CO2 capture ratio. So this will have an impact, of course, on the CO2 emission factors. We see that for the CLC, we will have the emission to the atmosphere will be approximately 30 kilograms of CO2 per megawatt hour of electricity, which is less than a third of what we have with the CFB coupled to CO2 capture, and which still is lower than the case of the NGCC coupled to CO2 capture. So this gives you what we have above here. We see the amount of CO2 that will be emitted to the atmosphere for this 200 megawatts of electricity thermal unit. You will have about 50 kilotons per year of CO2 to the atmosphere in the case of CLC, and this value will be much higher for the case of CFB and NGCC. And what another interesting thing to evaluate is the amount of CO2 that will have to be transported and then sent to the storage. So in terms of kiloton CO2 per year, so this is a CO2 that was captured and then that needs to be transported. So we have approximately the same value for CLC and CFB. So it's more than 1,000, it's very close to 1,500 kilotons per year. And we have a value which is much lower for the NGCC case. And this is just related, of course, to the nature of the fuel that is used. We have petcoke on one side, and we have natural gas, which has a much lower carbon content per energy content. So of course, it will produce lower CO2 amount. So now we can to the conclusion. So if we use, so we see that there are some very important different, and these are related to the nature of the fuel that is used. For the case of petcoke, the CLC will have the highest CO2 capture efficiency when we compare it to a conventional CO2 capture unit, which is designed with a need. And then when we consider the CO2 emitted to the atmosphere, CLC will yield the lowest amount. And when we have petcoke technology, CLC technology is the most efficient technology compared to CFB from that emissions perspective. And so it is the preferred technology when petcoke is used as a fuel, because it has higher net power efficiency, lower emissions, and higher CO2 capture efficiency. But natural gas and NGCC will yield the lowest amount of CO2 flow that will be transported and stored. So it is also something that needs to be taken into account. So this work is now available on the CHEERS website under the deliverable 5.2. So if you want to have more information about it, don't hesitate. You can just go to the website. Okay, thank you very much.
Thank you, Catherine. Okay, so now the process design is available. We will see how it has been economically assessed with the TEA. So I will let the floor to Vincent and Simon, Vincent from Total Energy and Simon from Sintef Energy to present this work.
So good morning, everybody. Can you hear me well? It's okay?
Yes, very well.
Okay, very good. So good morning, everybody in Europe, and good afternoon in China. So after presenting the modeling and the simulation, now we are entering the economic part. And Total Energy, represented by myself, with the help of an engineering company, were dedicated on the economics of the CLC and the CFB. And Sintef Energy, represented by Simon Roussanali, were more dedicated, concentrated on the cost of the NGCC and the full CCS chain. So can you change the slide, please? So as already described by Catherine, we can split the unit, the CLC, we concentrate on the CLC unit of the industrial case now, in three major sections. So we have the reactor section, reaction section described by Nicolas and Catherine. And then we have the flue gas treatment and the compression train for the CO2 and for the depleted air as well. And we have also a power generation section. So that's the three main section. For all this section, we have to look at all the battery limit, all what's going in, the inlet stream, the outlet stream. And with taken into account all these design parameters, we can size this equipment. And then at the end, you can see an example of the plant, the CLC plant that we design. So that's an overview from the top of the CLC plant with all the different parts. Next slide, please, Stefan. So to get the best and most accurate TEA, techno-economic assessment, we wanted to have the best figure for the CapEx and OpEx. And we selected few companies to get some quotes for different parts of the CLC. So for the section 1, the reaction section, we asked CMP AL company to quote us the manufacturing of the very large reactor, like Catherine says, 9 to 12 meter diameter, and also to quote their transport to the place where the unit will be built. Secondly, we ask also a refractory company named Damris to quote us for the implementation of all the refractory in all the reaction section. And this is a technology at 900 to 1000 degrees C. So all the reaction section is coated with the refractory. And we also ask Poitmill to give us some quotes regarding the preparation of the feedstock, the grinding and the drying of the feed. Then we concentrate on the flue gas treatment for both streams, as told by Catherine, for the depleted air that's match the regulation emission at stack, and also for the main flue gas, which is the CO2 at the outlet of the fuel reactor, to meet the EOR specification or enhanced oil recovery. And then we also ask Siemens to give us a quote for the steam turbine used for the industrial case. Next slide, please. Just a slide to concentrate on the CO2 flue gas treatment at the outlet of the flue gas of the fuel reactor. Sorry. So this it's quite specific because for a CLC you are in an oxy-combustion process, so you don't have any dilution of the contaminant you bring by the feed with the nitrogen. So it's nearly pure CO2. In this case, we use petcoke with 4% sulfur as a feed, and then you generate SOx and NOx and dust. And if you wanted to reach this EOR specification, like 1000 ppm for the NOx and SOx, and 1 milligram per millimeter cube for the dust, you need to have a quite robust flue gas treatment. With the company named Hammond, we looked a lot at this flue gas treatment. We did many schematics, and we end up with a quite consequent flue gas treatment. Furthermore, this flue gas treatment must cope with high water content in the CO2 because we are using steam into the flue gas, into the fuel reactor. And we need also to cope with the fact that there is no oxygen in this stream, and we need oxygen for the few units like the DSOx and the DNOx. So this, either you can buy the oxygen, either you can build an ISU. But just to say that when we took all these elements into account, we see that the flue gas treatment can account for 20% of the capex. So that's really to look at carefully when you will go into industrialization of this type of unit. So just as a reminder, Catherine told about the two application case, the refinery case and the power case. And we compare, as already told, to the CFB and NGCC. And for these two reference cases, so we did in each time two cases, the CFB with capture and also the CFB without capture to have a kind of reference case for the CFB, and the same for the NGCC with capture, MEA, and without capture to get the reference case. So this doubled the case we studied. For the technical assessment, economic assessment hypothesis, we used, so it's with 2019 price. It was planned to build this plant in Western Europe from grassroots. And so we use also a class 4 capex, and we use some contingencies for the project at 30%. We even use some process contingencies on the CLC technology at 20%, because it's quite new, it's not mature. For the other section of the CLC, we use only 5% for the process contingencies. Next slide, please. So we use a simple bottom-up approach to calculate the capex. So we come from a list of equipment and then come to the final capex. Yeah, you can go on, please. So this is the first KPI that I want to show you regarding the power case. So the KPI that we are displaying is the LCOE, or levelized cost of electricity. And if you look at the graph on the left, here you can see that the CFB LCOE, the CLC LCOE is about 100 euro per megawatt-hour. So it's a bit higher than the reference case in blue, which is the CFB without capture, but it's lower than the CFB with capture, with MEA in gray. And as already told by Catherine, we wanted to see where we are against other technology like NGCC using natural gas, which are the preferred technology to produce power. And we see that the NGCC plus capture in pink is at 92 euro per megawatt-hour, just below the CLC. So that's with the reference case for the prices of the feedstock, like the petcoke and natural gas. So set up in 2019. We looked at some sensitivities regarding what happened if we increase the natural gas by 50%, and we see that then the LCOE of the NGCC plus capture went over the CLC. If we look at the breakdown of this LCOE, on the left, you see that for the technology that's using solid feedstock, generally we have 1/3 CapEx, 1/3 OpEx, and 1/3 fuel cost. But on the right part for NGCC, you see that the fuel cost is nearly half of the LCOE. Next slide, please. The second KPI I would like to present you is the CAC, or the CO2 avoided cost in euro per ton of CO2. So this is for the power case. So the CAC is a delta of LCOE over a delta of emission. So you always compare yourself to a reference case. And we choose to present you the two reference cases. So we have a reference case, which is the CFB without capture. And the second reference case is the NGCC without capture. So if you look at the left graph, the first three columns are quite low. You see the CLC in yellow at 18 for the CO2 avoided costs. It's quite low because here the reference case is the CFB without capture, emitting a lot of CO2 because burning petcoke solid feedstock. On the right of this graph, you see the same CO2 avoided cost, but based on a reference case, which is NGCC without capture. So based on natural gas burning, and then emitting much less, twice as less, in fact, CO2 as the solid feedstock burning. So here that you see that the CAC is now near the 80-90 range. But you can see that the NGCC is just below the CLC. But the CLC is much better than the case CFB plus capture in both cases. You can move on, Stefan, please. So this is for the refinery case. Refinery case, I remember, is in cogeneration, 50 megawatt electric plus 100 ton per hour of HP steam produced. So difficult to use LCOE as a KPI, so we choose to use the NPV cost. And you can see that we have the same ranking that we see for the power case on the left, but for the graph on the right, which is the CO2 avoided cost, you see that the difference between CLC and NGCC increased. But we are still better than the CFB with capture. So next slide, please. So after looking at these two cases, we wanted to have some sensitivities. So we looked at, I will present two, and Simon will follow on. But for this power case, we looked at the oxygen carrier sensitivity. So basically, you have different type of oxygen carrier. You have some mineral oxygen carrier that can be quite cheap. And you can see this is mainly the left part of the graph. So you can see that the inventory change per year is not that affecting the LCOE. But on the right side, you can see the synthetic oxygen carrier price, like $5,000 per ton. And in here, you can see that you need to have an oxygen carrier with an inventory change less than 3 years to compete, or less than 5 years to compete with the CFB with capture, basically. So that was one sensitivity we would like to present. And the second one on the next slide is regarding the carbon capture rate. In fact, as Catherine said, we have planned a capture rate of 97.5. And we wanted to see what's happening if we decrease this capture rate, which is basically the efficiency of the carbon stripper. And so this is for the LCOE based on the power case with the reference case as the CFB without capture. So you see that even by decreasing to 85% the carbon stripper efficiency, you see that the CAC, or the CO2 avoided cost, is not increasing that much because of the reference, the CFB without capture emitting quite a lot of CO2. And on the right graph, you see that the CO2 emission in kilogram per megawatt is reaching the same level of the CFB with capture, around 100 kilogram per megawatt. So thank you very much for your attention. And now I will let the floor to Simon that will continue the sensitivities on the feedstock price.
Thank you, Vincent. So as Vincent is saying, we have also looked at impact of feedstock price, because we see that this is something which is different for the different process. And as we know, this is something that can change in the future, but also is also impacted by location and geopolitical aspects. So to that, what we have done is that we are looking at what we call a CO2 switching price between the CLC and the NGCC with MEA. So a bit similar to what you see before on the CO2 avoidance cost, except that here we compare the two concepts to the other. So we can then find a CO2 price, which says that if you're above that price, you will use, for example, here it will be the CLC, because the CLC have lower emissions. So it's if you have a price which is very high for CO2, then CLC will be better. And if you have a very, so we try to find that price. So here, this is what we illustrate on this figure, where on the Y, you see that we change the natural gas price between plus and minus 50%. And on the X, we change the petcoke price between plus and minus 100%. And we then use colors to kind of illustrate this. And basically, what they mean is that if it is a green colored, it means that the CO2 avoidance cost, which is calculated, is here to be in the favor of the CLC. So a green area means that the CLC will be better than the NGCC. The red area means the opposite. So the NGCC is going to be more cost efficient than the CLC. And what we have in orange, so this is an area where if we see that CO2 price will reach 200 euro or around 200 euro, which is, for example, the target that have been set by a few countries in Europe, for example, like Norway, for 2030. So this is an area also where the CLC will then be able to outperform the NGCC. So what we see here is that if you look at the case of the reference case of 0 and 0% change, so you find that before that it is an area where the NGCC outperformed the CLC. But if you're having cases where you have then higher cost, so the bottom two are the bottom left. So you see that if you have some higher natural gas price, if you have some lower petcoke prices, then it could be scenarios where the CLC could be better. And this can, for example, be relevant, for example, as you've seen that now the natural gas price have increased quite a bit. And also there's this question about future evolution of petcoke price, because as you know, some of the application for which it is currently used today might also change. For example, use of petcoke in the iron and steel sectors. If you go to the next slide, Vincent? Stefan. So that gives us some understanding, but also an important aspect for both the food chain performance and also for this comparison is also to look at the rest, what's happening after the capture part. So we did look at that using a tool that was developed by Center for Techno-Economic and Environmental Evaluation of CCS, called ICCS. And we then look at the scenario, which is what you have here in the figure. So after the plant, we consider that we will need to transport the CO2 via pipeline for over 100 kilometers before we liquefy it. And then that the CO2 will then need to be transported by ship over a bit less than 1,200 kilometers to a receiving facility. So this is in a way similar to transporting CO2 from the Belgium coast until a location like Northern Light. So this will be a dedicated infrastructure, and then we will then have afterward, once we arrive at the receiving terminal, a joint larger infrastructure, which will then have, for example, the reconditioning and the shared pipeline until injection. So as I said, the part on the left of this red line that you see is then dedicated, and we have assumed then that the part on the right will be a shared infrastructure of around 5 million tons of CO2. So something similar to the next phase, the second phase of Northern Light. If you go to the next slide, please. So here you see the cost, and I have put on the left part the power case, and on the right part the refinery case. And as part of this, what I forgot to mention is that we have looked at different scenarios. So in terms of the transport pressure, that low pressure or mid pressure, and also the size of the ship, both the size recommended by Northern Light and also the trying to optimize the size. And what we see from this scenario is that going to low pressure is the most efficient strategies, and if you're able to also optimize the size of the ship, that's also something which is beneficial. So we present the results for these cases. And so if you look at the LCOE, you see that, of course, this increase, but not so much. So if you recall, it's increased by around 10 euro per megawatt hour for the NGTC with solvents, and around 25 euro per megawatt hour for the CLC. So you have a larger increase for the CLC, and I'll get back to that. And in the case of the NPV, also you also have similar trend that you have a smaller increase for the NGTC, around also 10%, and a larger increase for the CLC. And the reason for this is that, as was mentioned earlier by Catherine, is that in the case of the CLC, you have a larger amount of CO2 which need to be captured for the same amount of energy produced, which also mean that you will have a higher cost for the transport and the storage and so on. If you go to the next slide so here we're also presenting the emission part. And you see similarly to before on the left, the power case, and on the right, the refinery case. And as we were discussing earlier, as we have different also capture ratio and emission rate per fuel. So what we were seeing is that the CLC was having quite lower emission than the NGCC when you focus on the capture part. But as you're also transporting more CO2, this also have an impact when you get the whole chain. So we see that this gap is narrowing down. So especially in the case of the power case, when you consider the emissions associated with, for example, electricity and fuel for liquefying the CO2 and transporting the CO2 by ship and reconditioning, you see that in the power case, the emissions are quite similar for this. So I think it was around half before, and now it's around 10% lower for the CLC. And in the refinery case, you see that there's an increase on the CLC, but the CLC is still then quite better emission-wise than the CLC. So I think it's around 45% of the emissions of the NGCC for the CLC. So this is also an important aspect to also consider when we were discussing about this what is the CO2 price that will make the switch between technologies. If you go to the next slide. Yeah. So based on this, taking the full chain approach, so we have redone the sensitivity that we were showing you earlier on the impact of the fuel cost on the switch between the two technologies. And as the CLC is, once you include the full chain, is increasing more in cost than the NGCC with solvent-based capture, and same for the emissions. Then we see that the gap that was the area that was before in green have decreased, but still a good area of where the CLC could be a better technology option. So this is especially if the petcoke price decrease, and if you remain with relatively high natural gas prices, which, for example, in Europe might be the case depending on the evolution in the coming years. So this is for the power part. And if you look at the refinery part, so we have also presented here the whole picture. And here what we see is that most of the area, the range of natural gas and petcoke prices that we have considered is leading to result where basically the NGCC with solvent-based capture will be the better option. And there's a very narrow window where CLC could be a cost-attractive part. So this is a less likely case where CLC will make sense compared to the previous one. If you go to the next slide. So to summarize from the result of the TEA part and the full chain part, so what we see is that CLC is clearly the competitive way of producing clean energy from petcoke compared to the CFD, which is both costly and a high emission options. Even with the solvent-based capture, it's still a very costly option. And if we look at the power case, so we see that if you just look at the CLC and the NGC comparison, we see that CLC is slightly more expensive than the NGC with carbon capture, with the reference natural gas and petcoke price that we have considered. And from that's the sensitivity, what it means is that basically we see that if we are able to have CLC plant being produced quite near to the storage, we see that CLC could be an attractive solution compared to the NGCC with CCS, if the gas prices are higher than what we consider as a reference, and that the petcoke prices are lower than what we consider as a reference. And in the case where we'll need to transport the CO2 over long distances, then this will decrease the competitiveness of CLC, because per amount of power produced, then you have more CO2 to transport with the CLC than the NGCC will capture. If you go, yeah. So for the refinery case, so what the result seems to indicate is that CLC is not a cost-efficient option compared to the NGCC with CO2 capture, with the reference natural gas and petcoke prices. And even when we are considering variations of this on this feedstock prices, we see that this does not seem to be a good option, especially when you include the CO2 transport. So unless petcoke is nearly free and that the gas prices are remain quite high, and that the CO2 storage the CO2 transport and storage costs are minimal, it is unlikely that CLC will be a cost-attractive solution in the refinery case. So what we see, to summarize a bit, so what we see is that with the reference assumption that have been taken for petcoke and natural gas prices, we see that CLC is not a competitive technology compared to the NGCC CO2 capture, that with higher gas prices and lower petcoke, it could be a better option. And this also goes into that discussion that the challenge that what to do with petcoke, we see that is a product which is going to be maybe more and more challenging for refinery to find a use for, because we see that, for example, in this where it was used, for example, in steel industry, they're also moving to different options. For example, using hydrogen, which means that there's going to be discussion about what to do with the petcoke. And if you are to then use the petcoke to produce energy, and that you have to do it with CO2 capture due to CO2 emission, due to CO2 tax or policy regime, or even company push toward reducing emissions, we then say that CLC is clearly the best option to use this fuel. So this will be an important question, I think, for this the development of CLC. So this is, I think, something that will likely come in the near future as a good solution. Okay, thank you.
Thank you, Simon. Thank you, Vincent. Thank you very much. So this concludes the results of the TEA. So now we will move on to the last part of this webinar, which is about life cycle assessments. So Elodie, the floor is yours.
Yes, so hello everyone. I'm Elodie Gawia, working for Total Energies, and I'm going to present the result of the life cycle assessment. The objective of the LCA was to assess the environmental performance of chemical looping combustion process to produce electricity. And the CLC process was compared to CFB combined with a CCS unit based on MEA. And also it was compared to a NGCC process combined with CCS unit also based on MEA. The functional unit used to compare these three processes is the production of 1 kilowatt-hour electric power. And the study, cradle-to-gate study, meaning that it includes the extraction of raw materials, but it does not include the use of the produced electricity. Next slide, please. So the methodology used, so I used the software CIMAPRO in association with EcoInvent database, and the method is the impact word plus method, both at midpoint and endpoint. Looking at the limitations of the study, first point is that construction and decommissioning of the plants were not taken in account. It was found in the literature that they have negligible effects on environmental impacts compared to the operating phase. So the LCA performed was focused on the operating phase. And second limitation is that transport and storage of CO2 was not taken in account in this LCA. So here are the different processes. So first is the CLC, where there is petcoke as input and compressed CO2 and electricity as outputs, with little CO2 direct emissions. Then there is CFB, also using petcoke as input and compressed CO2 and electricity as outputs, with CO2 as direct emissions. And then there is NGCC with natural gas as input, with compressed capture CO2 as output, and also electricity, and also CO2 as direct emission. Next slide. So here is the first result. So here we are focused on climate change, so meaning the GHG emissions. So we can see that with CLC, there is a reduction of GHG emissions by 43% when compared to CFB. We can also see that the main contributor of this GHG emission are due to the use of petcoke. So petcoke represents 66% of the overall emissions. And for CFB, you can see that the emissions are due to petcoke, to calcium carbonate, and also to the direct process emissions for 40%. Next slide. So here is a study based on the different CO2 capture rate for CLC. So here, the different capture rates studied were 97.5%, 95 and 93 compared to CFB and NGCC. And of course, you can see that depending on the CO2 capture rate, the emissions of the CLC vary. And so they are reduced by 43% compared to CFB with a 97.5% CO2 capture rate. And they are reduced to 29% with a 93% CO2 capture rate for CLC. So the CO2 capture rate is as a direct link with the climate change impact of the process. So here we looked through the LCA at other environmental impacts. So to have more data than only climate change, we also looked at mineral resource use, the ecotoxicity, the toxicity, the eutrophication, the particulate matter formation, the land use, and also the water scarcity. So here the results are present in percent change, and the result for the CFB are normalized to 100%. So CFB is in yellow, all the results as 100%. And then in gray, there are the CLC result, and in pink, the NGCC result. You can see that for the CLC result, the most environmental impact are less damage than with CFB. There is an increase for the mineral resource use, as the CLC process use both ilmenite catalyst and calcium carbonate. And also there is an increase in water scarcity impact because the CLC process use ammonia. We can also see that for the NGCC result, all the impacts are the lowest compared to both CLC and CFB. Next slide. Okay. So here is the result when we look at them endpoint, meaning that here the results are aggregated to look at the impact of the different processes on human health. And so you can see that with CLC, there is a reduction of impact on human health by 40% compared to CFB. And that within this impact, the main contributor are climate change, meaning that the CO2 emission are the main contributor to the impact on human health. And you can see also that for CLC result, there is the brown part, and due to particulate matter formation, and this is also due to petcoke. So the use of petcoke is really the main contributor to the impact on human health. And here again, we can see that NGCC has the lowest impact. Okay, and here again, so we are on the endpoint point of view, and this time we look at impact on ecosystem quality. And you can see that there is a decrease on impact on ecosystem quality by 52% with CLC compared to CFB. And the main impact is freshwater ecotoxicity, and it's less damage because there is less calcium carbonate used in CLC compared to CFB. And once again, we can see that NGCC has the better result for the impact on ecosystem quality, and this is due to the fact that in NGCC there is no petcoke use. So in conclusion, the LCA results have shown that the CLC process has reduced GHG emissions compared to CFB process, and this reduction is up to 43%. And the remaining emissions are mainly due to the use of petcoke. Overall, NGCC has the lowest impact on human health and ecosystem quality. And this is due to the fact that NGCC does not use petcoke. And as perspective, we can think about a switch from petcoke to biomass for CLC to improve the impact on the environment. So that's the end of my presentation. So if you have any question, I will be pleased to answer.
Thank you, Elodie. Thank you very much. So this presentation concludes the webinar. I didn't check the chat as I share my screen. Maybe we can.
There are 4 questions for now.
Okay, maybe we can take some time to answer these questions. So the first one is about orange trawler. So let's see. It's a question for you, Vincent.
Yeah, I think, thank you for this question. I think you are comparing the LCOE of the reference CFB case without capture at 85 compared to the NGCC case at 66 for the LCOE. And that's why we looked at the breakdown of the LCOE and we see the massive impact of the feed, or the natural gas price. So that's why we did some sensitivities on the price. And for sure, the petcoke price is lower than the coal price. And we estimated, for me, 80% of the coal price for the petcoke. And that was some hypothesis we took at this time to get this LCOE. So that's our hypothesis. And well, there is a little delta. Yeah.
I can comment. So the main thing that you cannot burn petcoke into a normal coal power plant. You have to use a CFB, and they are not very efficient. So this is why the costs are so high. So maybe you should remind the question every time, because I don't think that everyone see them. But the question was that Håkan was surprised that the LCOE of the NGCC is lower than that on the CFB with petcoke. LCOE of coal-fired power plant is really much lower than NGCC, and I expect that the petcoke price is even lower than that of coal. Could you please comment? So I think this is related to the fact that the CFB is not a very efficient way of using petcoke, but you don't have any other option. That or CLC.
Okay, thank you.
Then there was a question from Professor Lingfeldt on the fuel gas treatment for CO2. In this study, there is no oxygen polishing. The question is there any oxygen polishing at the end of the flue gas treatment? The question is no, it was not considered. The flue gas treatment that is already quite, how do you say, not massive or quite complex. And we think we could inject as few oxygen as needed for the units like DSOX and DNOx, but it is something that we will look at the demo plant to check if we need a CATOX or an oxygen polishing at the end or not. So this is something we continue to look at. But in this study, the CATOX or oxygen polishing was not considered. And it's true that for the EU air spec, there is an oxygen spec that we need to match.
Yes. A consequence of the previous point. Then another question from Rowan. LCA, petcoke is a residue from a refinery. Is it then appropriate to count indirect CO2 emission from petcoke for the combustion of petcoke?
So here in this study, petcoke was not considered as a residue, but as a co-product. So it has to take in account some of the indirect CO2 emission. So that's why there is indirect CO2 emission for the petcoke taken in account.
Thank you, Elodie. Then the last question from Zanab Nassif, OSP. So based on the webinar information which has been shared today, we would not recommend using petcoke as fuel either at power plants or refiners due to costs and emissions. So I'm not sure we can be so direct. Actually, as it was shown in the conclusion, taking the current price for petcoke and natural gas, this can be discussed. So it will depend on the fuel cost actually. So
and I think it will depend also, as you were saying, Stefan, on what is going to happen to the petcoke market, right?
Yeah.
Now the iron and steel sector is a big area for the petcoke market because it's it for reduction, but they're also moving away from that on the longer, or they aim to do it, move away from that with using, for example, hydrogen instead of the reducing agent. So that will likely mean that then the petcoke price could decrease also over time. And refinery produce quite a bit of this. So what do you do with that? Cannot burn it into normal coal power plants. If you use CFB, this is a bad option, as we see from the cost and the emissions. So then CLC could be a good way to do that. Then. So, but the economics will depend on how this price change.
Okay, thank you. There is no more question in the chat. Look at the discussion. No, it's okay. Okay, so we can take direct question if any. Hesitate to ask. Otherwise, you will ask for further information if you want after this webinar. So you can see our email address. So don't hesitate to contact directly the speakers if needed. And if you want to learn more about the Cheers project and follow the next step, so you can go to the Cheers website, Cheers YouTube channel, in which we will see this webinar. It will be uploaded in the coming days. And you could also find the previous webinars about the design study, the material studies, and the field studies. And we have also a LinkedIn page in which we provide information about the current status of the unit. So if you want to follow the startup of the unit, you will find some information on this page. So that concludes this webinar. So I would like to thank all the speakers. I would like to thank as well all the participants. Thank you very much. And we will see you again for normally the last webinar at the very end of the project, in which we will present the result from the demo unit operation. So thank you very much. Have a nice day and see you soon. Cheers.
Bye.
Bye-bye.
Bye.
Bye.
Goodbye.